Right now, at this exact moment, the fastest machine humanity has ever built is traveling through interstellar space at 38,000 miles per hour. It has been flying without stopping for nearly half a century, and at that speed, it will take another 76,000 years to reach the nearest star. Not to visit it, not to orbit it, just to pass near it. And that is not the reason we will never leave this solar system. That is just the beginning of the reasons. By the end of tonight, you are going to understand something that most people who talk about humanity's future in space have never been honest enough to say out loud. The barriers between us and the stars are not engineering problems waiting to be solved. They are written into the deepest laws of physics, biology, economics, and time itself, and every single one of them points toward the same conclusion. Before we get started, if you love exploring the deepest mysteries of space and the universe, take a second to like this video or subscribe. It's a simple action, but it helps this channel reach more minds like yours. Now let's begin. There is a number that should shake you to your core, but almost nobody ever stops long enough to let it sink in. The number is 424. That is how many light years away Alpha Centauri is, the closest star system to our Sun. 4.24 light years. It sounds small, it sounds manageable. We have names for things that are much larger. The Milky Way is 100,000 light years across. The observable universe spans 93 billion light years. By cosmic standards, 4.24 light years is the distance to the house next door. But let's convert that into something your brain was actually evolved to process. A light year is the distance light travels in 1 year. Light moves at 186,000 miles per second. In 1 second, a beam of light travels more than 7 times around the entire equator of the Earth. In 1 year, that beam of light covers roughly 5.88 trillion miles. Multiply that by 4.24 and the distance to the nearest star is approximately 24.9 trillion miles. 24.9 trillion miles to the closest neighbor, not to the interesting ones, not to the stars with confirmed rocky planets in their habitable zones, just to the closest star that exists, and it is almost exactly next door in the context of the universe. Now here is where the number stops being abstract and starts being terrifying. Our fastest spacecraft, Voyager 1, launched in 1977, has been flying through space continuously for nearly 49 years. As of April 2026, it is roughly 15.8 billion miles from Earth. That is genuinely astonishing, 15.8 billion miles. We built a machine that has traveled 15.8 billion miles, and it is still sending back data. And the team at NASA's Jet Propulsion Laboratory still has engineers who love it so deeply that some of them were not yet born when it launched. Voyager 1 is one of humanity's greatest achievements. It has reached interstellar space, the region beyond the Sun's bubble of charged particles. It is, by definition, outside the solar system's heliosphere, and it has barely started its journey to the nearest star. At Voyager's current speed, it would take approximately 76,000 years to reach Alpha Centauri if it were pointed in that direction, which it isn't. 76,000 years at our fastest to the closest destination. And this is the vehicle we built after 20,000 years of human civilization, after the Wright brothers, after Apollo, after every technological breakthrough our species has achieved. Our best effort at speed, deployed over nearly 5 decades of continuous travel, has closed less than 0.02% of the distance to the next star. This is the context in which every conversation about leaving this solar system must begin, not with optimism, not with inspiring speeches about humanity's destiny, with this number, because the distance is not just big, it is not merely difficult, it is so fundamentally enormous that it changes what is possible for any civilization that lives inside physics, which is every civilization that will ever exist. But let's go even further. Let's not just look at the nearest star. Let's look at the actual solar system we're trying to leave. Most people believe the solar system ends somewhere near Pluto. This is wrong by a factor of thousands. Pluto, the dwarf planet, orbits at an average distance of about 39 astronomical units from the Sun, 1 astronomical unit is the distance from the Earth to the Sun, roughly 93 million miles. So Pluto sits at roughly 3.6 billion miles from the Sun. That is indeed far away. It took the New Horizons spacecraft 9.5 years to fly there at roughly 31,000 miles per hour. But that is not the edge of the solar system. Beyond Pluto lies the Kuiper Belt, a vast donut-shaped region of icy objects extending from about 30 to 55 astronomical units. Beyond the Kuiper Belt lies the scattered disk, a sparser region extending to perhaps 100 or 150 astronomical units from the Sun. Beyond that lies the inner Oort cloud, also called the Hills cloud, a theoretical shell of icy bodies at distances of roughly 2,000 to 20,000 astronomical units. And beyond that lies the outer Oort cloud, the true edge of the Sun's gravitational reach, extending somewhere between 50,000 and perhaps 200,000 astronomical units from the Sun. At its outer edge, the Oort cloud sits roughly 2 light-years from the Sun, 2 light-years, nearly half the distance to the nearest star. And this structure, this vast spherical shell of frozen debris that our Sun has been gravitationally collecting for 4.6 billion years, is still part of the solar system. The solar system is not a neat little collection of 8 planets and a dwarf planet. It is a sphere of influence spanning up to 2 light-years in every direction. Leaving the solar system doesn't mean flying past Neptune. It means crossing a distance that would take our fastest spacecraft roughly 40,000 years just to reach the inner edge of the Oort cloud. Voyager 1 crossed the heliopause, the boundary where the Sun's charged particle wind gives way to interstellar space, in August 2012. That was a historic moment. Genuinely historic. The first human-made object in interstellar space. But even that milestone is misleading about what leaving the solar system actually requires, because Voyager 1 will not clear the gravitational influence of the Sun for roughly another 300 years just to enter the Oort cloud, and then will need another roughly 30,000 years to traverse it. We are not on the verge of leaving the solar system. We are not even close to being on the verge. We are in the earliest possible infancy of understanding what leaving would even mean. And now let's talk about why going faster is not the answer everyone assumes it is. Because this is where the conversation usually goes. People hear those numbers and they say, fine, Voyager 1 is slow by modern standards. We need better propulsion. We need nuclear rockets. We need fusion drives. We need antimatter engines. And they are right that we need better propulsion. But what almost no one appreciates, because the mathematics involved is so counterintuitive, is that the relationship between speed and energy is not linear. It is not even quadratic. As you approach the speed of light, the energy required to accelerate further increases toward infinity. And even well short of relativistic speeds, the numbers become so catastrophic that they reveal something profound about the nature of interstellar travel. Let us start with the rocket equation. This equation was derived in 1897 by a Russian scientist named Konstantin Tsiolkovsky, who worked out the relationship between a rocket's mass, its fuel, and the velocity it can achieve. The equation is elegant and devastating. To increase a rocket's velocity, you must carry propellant, but propellant has mass. And that mass also needs to be accelerated, which requires more propellant, which also has mass, which requires more propellant. The required fuel increases exponentially with the desired change in velocity. This is what engineers call the tyranny of the rocket equation. Here is a concrete example of why this matters for interstellar travel. Our best current rocket fuel, liquid hydrogen combined with liquid oxygen, has what is called a specific impulse of around 450 seconds. This is a measure of fuel efficiency. Using the Tsiolkovsky equation, if you wanted to accelerate a spacecraft to just 1% of the speed of light, about 1,060 miles per second, using the best chemical propellants we have, the ratio of fuel to payload mass becomes literally astronomical. you would need more fuel than there are atoms in any physically buildable structure. The rocket equation makes chemical propulsion not merely impractical for interstellar travel, it makes it mathematically impossible. Theoretical physicist Freeman Dyson stated this plainly decades ago. Chemical fuels are hopeless for interstellar travel. So what about nuclear propulsion? Nuclear fission rockets, where a reactor heats propellant to extreme temperatures and expels it for thrust, can achieve a specific impulse roughly 2 to 3 times better than chemical rockets. That sounds like a huge improvement. In the context of the rocket equation's exponential demands, it barely matters. You are still looking at fuel-to-payload ratios that require impractical masses to reach any meaningful fraction of light speed. Nuclear pulse propulsion, the concept explored in Project Orion in the 1950s and 1960s, where nuclear bombs are detonated behind a spacecraft and the shockwave is used for thrust, is more promising in principle. Theoretical calculations suggest an Orion-style ship could potentially reach 3 to 5% of the speed of light. At 3% of light speed, the journey to Alpha Centauri would take about 141 years. That is a generational ship, not a quick voyage, but it is at least within the conceivable. The problem is that Project Orion was shut down in 1963. Launching thousands of nuclear weapons into space was banned by the Partial Test Ban Treaty. Political reality buried what physics might have allowed. And even if we rebuilt it today, 3 to 5% of light speed still means journeys measured in centuries, which brings us to the biological problem. But before we get to biology, let us continue pushing on the physics, because there are more ambitious propulsion concepts than nuclear pulse, and understanding why they don't work is essential to understanding why the solar system is our permanent home. Fusion propulsion, which would harness the same process that powers stars by fusing hydrogen into helium and using the released energy for thrust, has been studied extensively. The efficiency gain over chemical propulsion would be enormous. Fusion propulsion could theoretically accelerate a spacecraft to perhaps 10 to 20% of the speed of light. At 10% light speed, the journey to Alpha Centauri takes about 42 years. That is within a human lifetime. That sounds almost manageable. But here is the problem with fusion propulsion. We don't have it. After more than 70 years of research and tens of billions of dollars invested in fusion energy research, we have achieved fusion reactions in laboratories. We have demonstrated net energy gain in carefully controlled settings, but we do not have a working fusion power plant anywhere on Earth. Converting from a laboratory experiment to a compact, reliable rocket engine capable of operating for decades is an engineering leap so vast that we cannot even estimate how long it will take. And if we cannot achieve controlled fusion in a power plant on Earth, under the most favorable possible conditions with the world's best equipment and unlimited maintenance access, the idea of doing it in a spacecraft operating autonomously for decades in the hostile environment of deep space with no possibility of repair or adjustment is something else entirely. What about antimatter? Matter and antimatter annihilate each other completely when they meet, converting 100% of their mass into energy. This is the theoretical maximum efficiency of any conceivable fuel. A kilogram of antimatter annihilating with a kilogram of matter releases roughly 180 times more energy than a kilogram of hydrogen undergoing fusion. With perfect conversion of that energy into thrust, an antimatter rocket could theoretically approach significant fractions of the speed of light. But let's look at what it would actually take to produce antimatter in useful quantities. The European Organization for Nuclear Research, known as CERN, produces roughly 15 nanograms of antihydrogen per year using the most sophisticated particle accelerators on Earth. That is 15 billionths of a gram. At that production rate, producing a single gram of antimatter would require roughly 70 million years. An actual interstellar spacecraft would need tons of it. And even if we somehow solve the production problem, which is not on any foreseeable technology roadmap, storing antimatter is perhaps even harder. It cannot touch any normal matter, or it annihilates instantly. You need to keep it suspended in magnetic fields indefinitely, in a perfect vacuum, with zero tolerance for equipment failure, because a single failure in containment means your entire fuel supply explodes with the force of nuclear weapons, destroying everything. The engineering required to maintain perfect antimatter containment for a journey lasting decades or centuries in the vacuum of interstellar space, experiencing cosmic radiation and particle impacts with no maintenance possible, with systems that have never been tested for more than a few seconds in laboratory conditions, is not a problem we are making progress on. It is not a problem that appears solvable within any time scale a rational person would discuss. Then there are the more exotic proposals. Breakthrough Starshot, the initiative announced in 2016 with funding from billionaire Yuri Milner and support from Stephen Hawking before his death, proposes sending tiny spacecraft weighing perhaps a gram, equipped with reflective sails and pushing them with ground-based laser arrays to 20% of the speed of light. At that speed, the journey to Alpha Centauri would take about 20 years. This is the most realistic near-term concept for reaching another star. But even this extraordinary proposal comes with caveats that reveal how far we are from anything like genuine interstellar travel. The spacecraft would be the size of a microchip. It could carry no crew. It couldn't slow down when it arrived. It would flash past Alpha Centauri at 20% light speed, gathering data for perhaps a few hours, and then continue into the void forever. The total data returned, limited by both the tiny power supply available and the 4-year travel time of the signal at light speed, would be measured in megabytes, the equivalent of a handful of photographs. The project is still in development, still facing significant engineering challenges, and even if it succeeds in its most optimistic form, it represents humanity looking at a star system through a keyhole, not traveling to it. So the picture that emerges from the physics of propulsion is this. With chemical rockets, interstellar travel is mathematically impossible due to the rocket equation. With nuclear fission, it remains impractical due to the same equation at the speeds required. With nuclear pulse propulsion, which we have banned for political reasons, journey times would be measured in centuries. With fusion propulsion, which we haven't built, journey times could fall to decades, but we are not building it. With antimatter propulsion, which is essentially magic in terms of our current capabilities, high fractions of light speed become theoretically achievable. With light sails and massive laser arrays, tiny uncrewed probes could make flyby missions lasting decades. None of these, not one, represents a path to sending humans to another star system. But here is where things get even darker, because all of the propulsion discussions have been happening in a context where we are imagining that if we could just go fast enough, we could get there. What most people don't realize is that even speed itself has a fundamental limit written into the fabric of reality, and that limit transforms the question of interstellar travel from difficult to perhaps permanently impossible for beings of our nature. Albert Einstein's special theory of relativity, published in 1905 and tested in thousands of experiments over the following century, establishes something extraordinary about the universe. The speed of light is not just the fastest speed currently achievable with our technology, it is the fastest speed that anything with mass can achieve ever, for any reason, using any mechanism, forever. This is not an engineering limitation, it is a structural property of space-time. As any object with mass is accelerated toward the speed of light, two things happen simultaneously. First, from the perspective of observers watching the object move, its mass effectively increases toward infinity. Second, the energy required to accelerate it further increases toward infinity. To reach exactly the speed of light would require infinite energy, which means it is not just impractical, it is impossible in the same way that a circle having 4 equal sides is impossible. Reality doesn't contain it. This fact reshapes everything. It means that even in the most optimistic possible scenario, even with technology we cannot yet imagine, human beings traveling between stars will always be experiencing a journey measured in years at minimum, and typically measured in decades or centuries. The nearest star at light speed, which is unachievable for anything with mass, takes 4 years and 3 months. The nearest star at 10% light speed, which would require energy exceeding anything our civilization currently produces, takes 42 years. The nearest star with a known Earth-sized planet that might be habitable, a world called Kepler 452b, lies approximately 1/400 light-years away. At 10% light speed, getting there takes 14,000 years. And yet, somehow, the speed of light barrier is not the most fundamental problem with leaving the solar system, because there is another constraint that operates entirely independently of our propulsion technology, and this constraint is one that no amount of engineering can solve. It is biological. Human beings evolved on a planet with a specific gravity, a specific magnetic field, a specific mix of atmospheric gases, and a specific solar radiation environment. We did not evolve for space. We are not adapted for it. Every system in the human body, from the circulation of blood to the density of bone to the function of the immune system to the wiring of the visual cortex, was shaped by millions of years of evolution under Earth-specific conditions. And when you remove those conditions, everything starts to break down. We have known this for decades from research on astronauts aboard the International Space Station. The data is unambiguous, thoroughly documented, and deeply concerning. In microgravity, without the constant mechanical stress that gravity places on bones, the body decides it no longer needs strong bones. It begins breaking them down. Calcium is released into the bloodstream and excreted. Bone density decreases at roughly 0.5% per month in the absence of countermeasures, approximately 10 times faster than the natural bone loss experienced by elderly people with osteoporosis. A 6-month mission to the International Space Station, during which astronauts exercise for 2.5 hours every single day specifically to combat this effect, typically results in a loss of 10 to 15% of bone density in key load-bearing structures. Some of that density never fully recovers even after years of rehabilitation on Earth. Muscle atrophy occurs simultaneously. Without the constant work of supporting body weight and moving against gravity, muscles weaken rapidly. Astronauts on 6-month ISS missions can lose up to 20% of their muscle mass despite their intensive exercise regimens. The muscles don't just shrink, they change structurally. The types of muscle fibers shift toward less efficient configurations. The results affect not just strength but coordination, balance, and the ability to perform complex physical tasks. The cardiovascular system also deteriorates. In microgravity, the heart does not need to work against gravity to pump blood to the brain. Over time, the heart weakens and changes shape. Blood pressure decreases, the vessels lose their tone. When astronauts return to Earth after long missions, many experience severe orthostatic intolerance, the inability to stand without fainting, because their cardiovascular systems have adapted to a world without the constant challenge of pumping blood upward against gravitational pull. Recovery takes weeks to months for shorter missions. For longer ones, the effects are more severe and take longer to reverse. The visual system presents another serious problem. Roughly 60% of astronauts on long-duration missions experience measurable changes to their vision. The leading explanation involves the redistribution of body fluids in microgravity. On Earth, gravity pulls fluid toward the feet. In space, that fluid redistributes toward the head, elevating the pressure inside the skull. This elevated intracranial pressure can deform the shape of the eyeball, swell the optic nerve, and alter the visual cortex. Some astronauts have experienced permanent vision degradation after returning to Earth. The technical term for this condition is spaceflight-associated neuroocular syndrome, and researchers have only been studying it seriously for the past decade. We still don't fully understand its mechanisms, and we certainly don't have reliable countermeasures. The immune system is disrupted. Studies have consistently shown that immune function degrades during spaceflight. Viruses that ordinarily remain dormant in the body, including members of the herpes virus family, such as the Epstein-Barr virus, the varicella-zoster virus, and cytomegalovirus, reactivate during spaceflight. The immune cells that normally keep these viruses in check appear to be less effective at doing so in the space environment. Wound healing is slower, the risk of infection appears higher, and some research suggests that cosmic radiation, which we'll discuss in detail shortly, further suppresses immune function through direct damage to the bone marrow where immune cells are produced. Sleep is disrupted in space. The human circadian rhythm evolved to be regulated by the natural cycle of day and night on Earth. In low Earth orbit, astronauts experience 16 sunrises and sunsets every 24 hours as the ISS circles the planet. Sleep quality in microgravity is documented to be significantly worse than on Earth. Insufficient sleep compounds virtually every other physiological problem, degrading cognitive function, immune response, emotional regulation, and physical recovery. And in deep space, far from the circadian cues our biology depends on, the problem is expected to be even more severe. Now take all of these problems, individually well documented in astronauts spending 6 months or at most 1 year in low Earth orbit, still partially protected by Earth's magnetic field, still receiving regular resupply missions, still in contact with mission control with a communication delay of only a few seconds, still capable of emergency return to Earth within hours if necessary. Take all of those problems and extend them over the duration of an actual interstellar mission. The minimum conceivable journey time to Alpha Centauri, using propulsion systems we do not yet have, is roughly 40 years at 10% light speed. That is 40 years in microgravity or in whatever artificial gravity system we might be able to engineer, which brings its own complications. 40 years of elevated radiation exposure, 40 years of recycled air and recycled water and processed food, 40 years in a confined space with the same small group of people. 40 years with no possibility of return and no help from Earth if anything goes wrong. Not 40 years like the ISS, where 8 people can work in a structure the size of a football field, and where a medical emergency can be addressed with evacuation within hours. 40 years in a vessel that will be the crew's entire universe, with whatever medical supplies and equipment were loaded before departure, with communication delays that start at minutes and grow to years, with complete and permanent separation from Earth and everyone on it. No human being has ever done anything remotely like this. The longest single spaceflight in history was 437 days, set by Russian cosmonaut Valery Polyakov on the Mir space station in 1994 and 1995. That mission required extraordinary dedication and resulted in significant physical deterioration. Polyakov needed extensive rehabilitation before he could walk normally again. 40 years is 33 times longer. We have absolutely no data on what the human body does under those conditions, and everything we do know points toward the conclusion that the human body was not designed to survive them. Let's be specific about the radiation problem, because it deserves its own examination, and it may be the most insurmountable of all the biological barriers. On Earth's surface, we are protected from the most dangerous forms of space radiation by 2 shields operating simultaneously. First, Earth's magnetic field deflects a large fraction of the charged particles in the solar wind and cosmic rays before they reach the atmosphere. Second, Earth's atmosphere, which is equivalent in terms of radiation shielding to approximately 10 meters of water, absorbs and scatters the radiation that gets through the magnetic field. Together, these 2 shields reduce our annual radiation exposure to roughly 0.3 millisieverts, a unit of biological radiation dose from natural cosmic sources. Aboard the International Space Station, which orbits within the outer reaches of Earth's magnetic field, and is partially shielded by the planet itself blocking radiation from below, astronauts receive roughly 150 to 200 millisieverts per year, approximately 500 to 600 times higher than on Earth's surface. A 6-month mission exposes an astronaut to roughly 75 to 100 millisieverts total. In deep space, beyond the protection of Earth's magnetosphere, the radiation environment is categorically different. There are two primary sources of concern. Solar particle events are sudden bursts of high-energy particles emitted by the Sun during solar flares and coronal mass ejections. A major solar particle event can deliver hundreds of millisieverts of radiation in a matter of hours. Without heavy shielding, such an event during an interstellar transit could cause acute radiation sickness, with symptoms including vomiting, hemorrhaging, suppression of bone marrow function, and death. These events cannot be predicted more than a few days in advance, and given the communication delays involved in interstellar travel, there would be no way to receive a warning from Earth in time to matter. The second source is galactic cosmic rays. These are high-energy particles, mostly protons and atomic nuclei, accelerated to near-light speed by supernova explosions and other violent cosmic events throughout the Milky Way. They come from every direction simultaneously, can penetrate essentially any material that a spacecraft could reasonably carry, and represent a continuous background exposure that cannot be turned off. In the inner solar system, the Sun's magnetic field embedded in the solar wind deflects a significant fraction of galactic cosmic rays, a phenomenon called the solar modulation of cosmic rays. But as you travel beyond the heliopause into true interstellar space, even that protection disappears. Galactic cosmic rays reach their maximum intensity in interstellar space. NASA's career radiation exposure limit for astronauts has historically been calculated based on a 3% increased risk of developing fatal cancer, adjusted for age and sex. The specific number varies, but for a middle-aged astronaut, the lifetime limit is roughly 800 millisieverts for women and 1,000 millisieverts for men. A 40-year interstellar voyage during which the crew would receive approximately 600 to 900 millisieverts per year would expose each crew member to somewhere between 24,000 and 36,000 millisieverts, exceeding their lifetime limit 30 to 40 times over. And this doesn't account for solar particle events, which could add hundreds more millisieverts in a matter of hours, unpredictably. The biological consequences are severe. Elevated cancer risk is the most obvious concern, but it is not the only one. Cosmic rays, particularly the heavy nuclei component of galactic cosmic rays, have a quality of damage that distinguishes them from other forms of radiation. When a heavy nucleus traveling near the speed of light passes through biological tissue, it leaves a track of ionization damage along its entire path. This damage is qualitatively different from other radiation exposure. Studies in animal models have shown that exposure to cosmic ray-equivalent radiation causes cognitive impairment, including memory loss, reduction in neuronal connectivity, and behavioral changes consistent with accelerated brain aging. NASA researchers have referred to this as a potential space brain problem, and it represents a threat not just to the health of crew members, but to their ability to make the complex decisions required to operate a spacecraft and survive in a hostile environment for decades. We have no proven method to protect against galactic cosmic rays with practical spacecraft shielding. Passive shielding helps, but diminishing returns set in quickly. Adding more mass to shield against cosmic rays requires more fuel to accelerate that mass, which requires more fuel, following the rocket equation toward impractical extremes. Active magnetic shielding has been proposed, but requires superconducting magnets generating enormously strong fields maintained indefinitely in space with power demands that would require dedicated nuclear reactors and mechanical reliability over decades that no engineer has been able to demonstrate. The problem of cosmic ray exposure for long-duration deep space travel is not solved. There is no credible timeline for it being solved. All of this, the bone loss, the muscle atrophy, the cardiovascular changes, the vision problems, the immune suppression, and the radiation exposure, these are the problems we know about from a few decades of operating a space station in low Earth orbit, with regular crew rotations and extensive support infrastructure. We are dealing with them in astronauts who are extraordinarily healthy to begin with, subjected to rigorous selection processes that eliminate anyone with a predisposition to these problems, exercising intensively for hours every day, taking pharmaceuticals, using the best medical monitoring equipment available, and returning to Earth within 6 months to recover. Imagine the physiological state of a crew member on an interstellar voyage after 20 years, after 30, after 40, and we have not yet talked about the psychological dimension, which may be the most fundamental human barrier of all. The psychological challenges of extended isolation in a confined environment with a small group of people are well documented in terrestrial analogues. Antarctic research stations, submarines, cave isolation experiments, simulated Mars missions conducted on Earth all have demonstrated consistent patterns. In the early phases, excitement and novelty carry people through the discomfort. Over time, as novelty fades and routine becomes oppressive, psychological effects begin to accumulate. Minor interpersonal conflicts that in normal social life would be resolved by distance, by the ability to simply walk away from someone who irritates you, become major sources of stress when you cannot escape. The technical term for the psychological deterioration seen in isolated, confined environments is the third quarter phenomenon. People typically manage reasonably well in the first half of a mission, but psychological health tends to deteriorate significantly in the second half as the end feels simultaneously closer and more impossibly distant. Now imagine that third quarter phenomenon playing out not over 6 months but over decades in a vehicle that is the crew's entire universe, headed toward a destination from which there is no return, after leaving behind everyone and everything the crew members have ever known, with no ability to speak to anyone on Earth in real time. The communication delay to Alpha Centauri at 4 light years is 4 years and 3 months, one way. If a crew member wants to tell their family they arrived safely, that family will not know for over 4 years. A conversation that would take 2 minutes on Earth takes more than 8 years for a single exchange, and by the time the reply arrives, the context will have completely changed. The people they left behind will have aged, changed, and many will have died, all in events that the crew will learn about years after they occurred. The psychological burden of this disconnection, of existing in a bubble of solitude utterly severed from the flow of human civilization, cannot be overstated or fully modeled. We have never put human beings in this situation. We have no idea what it does to a mind over decades, but every piece of evidence from shorter isolation studies suggests the effects are severe. Depression, anxiety, cognitive distortions, interpersonal breakdown, and in extreme cases, violence and suicide, all are documented outcomes of isolation environments far less extreme than what a genuine interstellar voyage would impose. And there is a deeper psychological problem that is rarely discussed honestly. An interstellar mission is necessarily one way. This is not a defeatist statement, it is a consequence of physics. If you accelerate a spacecraft to 10% of light speed for a 40-year journey to Alpha Centauri, the fuel required to decelerate upon arrival and the fuel required for the return journey adds exponentially to the total mass you need to carry when you leave Earth. The rocket equation demands it. You would need to carry fuel for 4 velocity changes, accelerating outbound, decelerating at the destination, accelerating back toward home, and decelerating on return. Each velocity change is exponentially expensive in terms of fuel mass. The total spacecraft mass required for a round trip becomes impractical at any level of technology we can meaningfully envision. This is why serious discussions of interstellar missions, even in academic contexts, focus on one-way colonization. Not round trips, you go, you don't come back. The people who volunteer know they are saying goodbye to Earth forever, that their children will grow up in a spacecraft, that their grandchildren may never see a planet, that the destination they're headed toward might be inhospitable, and that if anything goes wrong at any point during the journey, there is no rescue. No rescue mission is possible on any relevant timescale. A rescue vessel launched from Earth the moment a problem was detected would need over 40 years to arrive, and by then, any acute crisis would have resolved one way or the other, almost certainly the other. This is not exploration in any sense that resembles what the word has historically meant. When Columbus set sail across the Atlantic in 1492, the journey was dangerous and the destination uncertain, but the round trip was conceivable, and the crew retained some hope of return. Even the Antarctic explorers of the early 20th century, who undertook missions with genuine life-threatening risk, could in principle be rescued, and those who survived returned to describe what they found. An interstellar colonization mission is categorically different. It is permanent exile entered voluntarily, from which there is no rescue, no return, and no second chance. Some people are willing to accept this. Mars One, the ill-fated private project that proposed sending colonists on a one-way mission to Mars, received over 200,000 applications. The human capacity for adventurous sacrifice is real and should not be dismissed. But Mars is 140 million miles away at its closest. Alpha Centauri is 24.9 trillion miles away. The scales are so different they represent different categories of challenge, not just different quantities of the same challenge. Now let's talk about time, because the time dimension of interstellar travel deserves its own examination, and it reveals something that the physics and biology discussions don't fully capture. The problem is not just that interstellar journeys take a long time. It is that they take so long that everything changes in ways that make the mission itself incoherent over its duration. Consider a 40-year voyage. You leave Earth in, let's say, 2070 with the absolute best technology humanity has been able to develop by then. You arrive at Alpha Centauri in 2110. The technology aboard your ship, which you cannot replace or upgrade, because you are in interstellar space with no resupply possible, is 2070 technology. Meanwhile, back on Earth, 40 years of continued technological development have occurred. It is entirely possible, given historical rates of technological progress, that within a few decades of your departure, someone on Earth develops a faster propulsion system and launches a second mission that overtakes yours and arrives before you do. The crew who launched first, who sacrificed everything to be pioneers, might arrive to find that a faster ship launched 30 years after them is already there. This is not a hypothetical. It is an actual logical problem with interstellar missions given any reasonable model of technological progress. The people who go first will almost certainly be traveling in the slowest vessels ever sent to that destination, because every subsequent generation will have better propulsion. The more you wait, the faster you can go, which means the optimal launch time is always in the future. But the future recedes as fast as you approach it. This is why no interstellar mission has ever been launched, and it is part of why none ever will be, because the planning horizon required to commit to such a mission is longer than any political institution, funding body, or human motivation structure can sustain. Governments change every 4 to 8 years. Corporate planning horizons are measured in quarters, not decades, let alone centuries. The scientific community is not immune to changing priorities. A mission requiring consistent institutional commitment over 40 to 400 years, depending on propulsion technology, has never been successfully managed in human history. The longest-standing scientific programs are perhaps a few decades in duration. The Manhattan Project, which produced the atomic bomb in 3 years, is considered a staggering feat of institutional focus. An interstellar mission would require that level of focus for 10 or 20 times as long. And this problem is not limited to the launch phase. An interstellar spacecraft operating for 40 to 400 years needs systems that remain functional without maintenance for that entire duration. Every mechanical system fails eventually. Every electronic component degrades, lubricants dry out, seals fail, circuits corrode, programming develops errors. The International Space Station, which operates only 250 miles above Earth with continuous resupply missions and the ability to send repair crews, requires constant maintenance by expert astronauts to remain functional. It would not survive 40 years without that maintenance. No spacecraft ever built has survived that long in operational condition. Voyager 1 is still transmitting after nearly 50 years, which is miraculous, but it is doing so with increasingly limited functionality, running on a few instruments kept alive by the last dregs of a plutonium power source, having shut down virtually everything else to conserve power. It is not exploration ready. It is barely alive. Now let's take all of these problems together: the propulsion barriers, the radiation problem, the physiological deterioration, the psychological barriers, the one-way nature of the mission, the institutional commitment problem, and the system's reliability problem. And let's ask a simple question. Given all of this, where does humanity's future actually lie? The honest answer, the answer that the physics and biology force us toward if we are willing to look at them clearly, is this: our future lies in this solar system. Not on Earth alone, but within the gravitational reach of our Sun. And what is startling, once you begin to think about it clearly, is how staggeringly large and how remarkably rich the solar system actually is. The solar system is not 8 planets and a collection of smaller objects. It is a civilization-sustaining environment of almost incomprehensible scale. Let's do something different here and actually look at what the solar system offers, because most discussions of space exploration talk about it as a stepping stone to somewhere else, when in fact it may be the entire destination. The inner solar system, Mercury, Venus, Earth and Mars, together with the Moon and the asteroid belt, contains an enormous diversity of environments and resources. Mars alone has a surface area roughly equal to Earth's total land area. It has ice at its poles, minerals of virtually every type in its crust, seasonal variation, and enough of an atmosphere to provide some protection from radiation, while being thin enough that terraforming or habitat construction are at least conceptually feasible. Venus, despite its hellish surface, may have regions in its upper atmosphere at roughly 50 to 60 kilometers altitude where temperatures and pressures are similar to Earth's surface, and where floating habitats made of breathable air would actually provide buoyancy in the denser carbon dioxide atmosphere below. Mercury has permanently shadowed craters near its poles where water ice has been confirmed, along with year-round solar power availability in equatorial regions that could support industrial operations. The asteroid belt between Mars and Jupiter contains an estimated 1 to 2 million asteroids with diameters greater than 1 kilometer, along with hundreds of thousands of smaller objects. These asteroids collectively contain enormous quantities of iron, nickel, cobalt, platinum group metals, and other minerals that are relatively rare on Earth's surface but far more accessible in space. The total mass of all the minerals in the asteroid belt, if extracted and processed, would be sufficient to build orbital habitats housing trillions of human beings. The theoretical physicist Gerard O'Neill calculated in the 1970s that with asteroid-based resources, rotating cylindrical space habitats could be built that would provide artificial gravity, natural lighting, and living space for populations far exceeding anything Earth can support. The total interior surface area available from asteroid materials, built into O'Neill cylinders at a spacing where each resident has living standards comparable to modern Earth, would be thousands of times Earth's total surface area. Then there is the outer solar system. Jupiter, the largest planet, has 4 large moons that are worlds in their own right. Io, the most volcanically active body in the solar system, generates enormous amounts of heat through tidal flexing. Europa has a global ocean of liquid water beneath its icy crust, kept liquid by the same tidal forces, potentially containing more than twice the volume of all of Earth's oceans combined, with hydrothermal vents at its ocean floor that could support life similar to the extremophile ecosystems found around thermal vents in Earth's deep oceans. Ganymede, the largest moon in the solar system, bigger than the planet Mercury, has its own magnetic field and a subsurface ocean. Callisto is heavily cratered but geologically stable and might make an excellent base of operations for exploring the Jovian system while being far enough from Jupiter's radiation belts to protect inhabitants. Saturn offers Titan and Enceladus as the crown jewels of the outer solar system's habitability potential. Enceladus, as the Cassini mission confirmed definitively, is actively venting water vapor, ice particles, and organic molecules from a subsurface ocean through cracks in its southern polar ice. The plumes contain hydrogen gas, carbon dioxide, methane, and complex organic compounds. The presence of liquid water, organic chemistry, and an energy source from tidal heating makes Enceladus one of the most promising places to search for life in the solar system, and one of the most intriguing potential sites for long-term human presence. Titan, with its thick nitrogen atmosphere, its surface temperatures kept below -290 degrees Fahrenheit by its distance from the Sun, its lakes and seas of liquid methane and ethane, and its complex organic chemistry present throughout its atmosphere and on its surface, is so strange and so alien that it demands study that only human presence could fully provide. Titan also has an atmospheric density that is 4 times Earth's at the surface, and a surface gravity of only about 1/7 of Earth's, which together mean that human-powered flight on Titan is physically possible with only modest extensions of our existing technology. Neptune's moon. Triton orbits retrograde, moving in the opposite direction of Neptune's rotation, which means it was captured from the outer solar system rather than forming in place. It has geysers erupting nitrogen from its surface, driven by a temperature so close to absolute zero that solar heating can still sublimate the nitrogen ice. The Kuiper Belt, of which Triton may once have been a member before its capture, contains Pluto and its companion, Charon, along with thousands of other objects that preserve pristine samples of the material from which the solar system formed 4.6 billion years ago. The point of this inventory is not simply that there is interesting science to do within the solar system. The point is that the solar system contains enough volume, enough resources, enough diversity of environments, and enough scientific richness to occupy human civilization not for centuries, but for millennia, potentially for millions of years, without ever needing to venture to another star. The solar system, properly understood and properly developed, is not a cage, it is an empire. And developing that empire, building the infrastructure of a genuinely spacefaring civilization within our own solar system, might actually be what makes life in the universe sustainable for humanity in the long run in a way that premature interstellar ambition never could. Let's talk about what it would actually take to become a true solar system civilization. Because the gap between where we are today and being a civilization that has genuinely mastered the solar system is already enormous, and bridging that gap is the actual work ahead of us, not the fantasy of flying to other stars. Today, in 2026, humanity's permanent presence in space consists of the International Space Station housing a crew of 6 to 7 people in low Earth orbit at 250 miles altitude. We have visited the Moon with 12 humans over 3 years, ending in 1972. We have sent robotic missions to every planet, to Pluto, to numerous moons, to comets, and to asteroids. We are planning to return humans to the Moon under the Artemis program, with crewed lunar surface missions targeted for the late 2020s. Elon Musk's SpaceX has ambitions to establish a human presence on Mars using its Starship rocket system within the coming decade or two. NASA and other agencies have Mars as a long-term destination in their planning documents. All of this is genuine progress, and it is thrilling in its own right. But measured against the scale of the solar system, It is as if the entire history of human seafaring consisted of paddling a rowboat a few hundred yards from shore. The real work of solar system civilization is still almost entirely ahead of us, and the challenges that work involves are themselves staggering, which is both humbling and, in a certain sense, reassuring, because it means there is an enormous amount to do and to discover without leaving. Consider the challenge of radiation shielding for deep space habitats. This problem doesn't go away even within the solar system. Beyond the protection of Earth's magnetosphere, radiation exposure becomes a serious issue. Solving it for permanent habitation on Mars, on the Moon, on asteroids, or in free space requires developing either extremely effective passive shielding materials, reliable active magnetic shielding, or biological countermeasures such as radiation-resistant pharmaceuticals or genetic modifications that enhance the body's radiation repair mechanisms. All of these are active research areas. None of them has been solved. Solving them would not just make Mars colonization safer, it would make all of the biological barriers to deeper solar system exploration less severe and would represent progress toward understanding what human bodies can endure in space, knowledge that is essential regardless of any interstellar ambitions. Consider the challenge of closed-loop life support systems. Today's best life support on the International Space Station recycles roughly 93% of water from all available sources, including humidity in the air, urine, and condensation from the crew's breathing. That remaining 7% is a problem only manageable because the ISS receives regular resupply missions. A Mars mission, where Earth return capability exists, but only on a 2-year cycle, aligned with favorable planetary alignment, needs something much closer to 100% recycling. A permanent deep solar system habitat needs essentially perfect closed-loop recycling of air, water, and nutrients with no possibility of external resupply at all. Building truly closed ecological life support systems that can function at 100% efficiency for years and then decades through various failure modes with self-repair capability is one of the genuinely hard engineering problems in front of us. It has not been solved. Solving it is necessary for Mars. Solving it is necessary for the asteroid belt. Solving it is necessary for any outer solar system presence. And solving it is also, incidentally, a capability that would be required for any interstellar voyage. But the work is the same. Consider the challenge of in situ resource utilization, the ability to use materials found on location rather than shipping everything from Earth. On Mars, this means extracting water from ice deposits, producing oxygen from the carbon dioxide atmosphere using processes like electrolysis and the Sabatier reaction, mining iron and other metals from the Martian regolith, and eventually synthesizing pharmaceuticals, electronics components, and industrial materials from locally available resources. SpaceX has designed the Starship vehicle around the assumption that liquid methane and oxygen can be produced on Mars from the carbon dioxide atmosphere and water ice, enabling vehicles to refuel for the return trip rather than carrying all their propellant from Earth. NASA's Perseverance rover has demonstrated oxygen production from the Martian atmosphere using an instrument called MOXIE, Mars Oxygen In Situ Resource Utilization Experiment, confirming the basic principle in practice for the first time in 2021. But scaling from a laboratory demonstration to producing the tens of tons of propellant required to launch a vehicle from Mars before any crew even arrives is an engineering challenge of the first order. And this is just Mars, the easiest target in the solar system by most measures. Developing similar in situ resource utilization capability for the asteroid belt, for the moons of Jupiter and Saturn, for the trans-Neptunian region, represents decades or centuries of engineering work that is both necessary and genuinely exciting regardless of any ambitions to leave the solar system. The communication challenge is itself underappreciated. Today's deep space network manages communication with spacecraft throughout the solar system using ground-based radio telescopes. Communication with Voyager 1 involves a round-trip signal time of over 46 hours and uses some of the most sensitive radio receiving equipment on Earth just to detect a signal emitted at a power level of 22 watts, comparable to a dim light bulb. As human presence expands deeper into the solar system, the communication infrastructure required to support it grows dramatically in both scale and complexity. Managing operations on the surface of Titan, where signals take approximately 80 minutes one way to reach Earth, requires developing autonomous systems capable of making real-time decisions without guidance from Earth, which is a profound challenge in artificial intelligence, robotics, and systems engineering. Expanding human civilization through the solar system requires solving this challenge at every distance and in every environment. Now let's come back to the central question. Given all of this, given all the barriers, all the challenges, all the physical laws that conspire to keep us within the solar system forever, what does this mean for humanity? Is it depressing? Is it a limitation that diminishes us? Or is it something else? This is where the conversation becomes genuinely philosophical, and where the honest examination of our cosmic situation reveals something that is not despairing, but in a certain sense, liberating. The solar system is not a cage. It is not a prison. It is not a limitation imposed on us by a universe that wants to keep us small. It is the environment in which life arose, the environment in which our civilization developed, and the environment in which the arc of our future will play out. Everything that has ever mattered to a human being happened within this solar system. Everything beautiful, everything terrible, everything transcendent in human experience exists within the gravitational reach of a single yellow star. And this solar system, this empire of rocks and gas and ice and light, extends for roughly 4 light years in every direction, contains enough material to build habitats for populations that dwarf anything Earth can support, harbors environments where liquid water may exist beneath miles of ice on moons orbiting planets so remote they were discovered only in the last few centuries, and has been here, evolving and changing for 4.6 billion years. There is a school of thought popular in certain corners of the space community that treats the solar system as merely a launching pad, a temporary base camp before humanity's real destiny among the stars. This view tends to assume that because we can imagine flying to other star systems, we should be working toward flying to other star systems, and that any conversation about the impossibility of doing so represents a failure of vision or ambition. But this view fundamentally misunderstands what the barriers actually are. They are not barriers of engineering or technology. They are barriers of physics, of biology, of time, and the appropriate response to true physical limits is not to deny them, but to understand them clearly and then ask what extraordinary things become possible within those limits. Consider what a genuinely mature solar system civilization would look like. Not in the near future, not within the lifetime of anyone alive today, but on the time scale of centuries. A civilization that has mastered fusion energy, that can accelerate spacecraft to perhaps 10% of the speed of light, that has solved the radiation problem, that has developed closed-loop life support systems adequate for multi-decade voyages, that has established industrial operations in the asteroid belt, that has permanent scientific outposts on the moons of Jupiter and Saturn, and that has developed the robotic and artificial intelligence infrastructure needed to explore and utilize the outer solar system. What does that civilization look like? It is a civilization spread across a volume of space enormously larger than any human being today can viscerally comprehend. It contains more living space than Earth could provide to every human who has ever lived, multiplied by thousands. It has access to essentially unlimited material resources because the asteroid belt and outer solar system contain far more iron, silicon, carbon, nitrogen, oxygen, hydrogen, water, and precious metals than will ever be needed by any human population. It has energy to spare, either from fusion reactions using hydrogen extracted from the gas giants, or from carefully managed use of the sun's output through the kinds of large-scale solar collection systems that a truly advanced civilization would be capable of building. And this civilization, by any meaningful measure, is immortal in ways that earthbound humanity is not. A single asteroid impact, a supervolcanic eruption, a sufficiently virulent pandemic, a nuclear exchange, a runaway greenhouse effect, any of these could end or severely damage human civilization on Earth. A civilization distributed across dozens of habitations throughout the solar system is essentially immune to any of these threats. No single event can reach everywhere simultaneously. The redundancy of a genuinely solar system-spanning civilization provides exactly the kind of existential insurance that many people imagine requires interstellar travel to achieve. You don't need to reach another star to ensure that humanity cannot be wiped out by a single catastrophe. You need to reach multiple independent habitations within the solar system, which is a vastly more achievable goal. Furthermore, a civilization of this kind, one that has existed for centuries and has solved the genuinely hard problems of radiation management, closed-loop life support, in situ resource utilization, and reliable long-duration space systems, would know exponentially more about the challenges of space habitation than we do today. The medical community would have studied the effects of space on the human body for generations and developed interventions we cannot yet imagine. Genetic therapies, pharmaceutical countermeasures, selective breeding or genetic modification for enhanced radiation resistance, or entirely new biological approaches to sustaining human health in novel environments. The engineering community would have built and maintained space systems across timescales long enough to understand failure modes that we currently cannot even anticipate. And this civilization, unlike us, would be genuinely positioned to make honest, informed, and potentially rational assessments of interstellar travel. Where we are today trying to decide whether to attempt an interstellar mission is like asking people in the year 1450 to decide whether to attempt a mission to the moon. The technology gap is so enormous that the conversation cannot be honest. We don't know what we don't know. A civilization that has spent 500 years developing space technology incrementally, solving each problem as it becomes soluble, would approach the question of interstellar travel with far more relevant knowledge than we can bring to it today. Now let's address something that comes up inevitably in conversations like this one, and it deserves a direct response. What about the future sun? In roughly 5 billion years, the sun will exhaust the hydrogen in its core and expand into a red giant, engulfing Mercury and Venus, and possibly reaching Earth's orbit. Earth will almost certainly be rendered uninhabitable long before that, probably within a billion years, as the slowly brightening sun increases its energy output enough to drive a runaway greenhouse effect similar to what Venus experienced billions of years ago. This is sometimes cited as an argument for why humanity must eventually develop interstellar capability. If we want to survive the death of our sun, we must eventually leave this solar system. This argument is true in the very long run, but it conflates timescales in a way that is intellectually misleading. A billion years is so much time that it is essentially meaningless from any current planning perspective. In a billion years, if our civilization survives, we will be as different from current humanity as current humanity is from single-celled organisms that existed a billion years ago. The people, or post-people, or whatever we become in a billion years, will make their own decisions about what to do when the sun starts to threaten their existence. And by that point, if we have managed to remain a technologically capable civilization for a billion years, the technological landscape of what is possible will be so completely different from anything we can predict that it is genuinely meaningless to plan for it today. We cannot plan for problems a billion years in the future any more than bacteria planning for the Cretaceous-Paleogene extinction could have been useful. The case for developing solar system civilization now is not about the eventual death of the sun. It is about the much nearer-term reasons for expansion, including the existential risk reduction that comes from distribution across multiple habitats, the scientific wealth to be found throughout the solar system, the resource base that supports growing human populations and rising living standards without destroying the Earth's biosphere, and the sheer intrinsic value of exploration and discovery as expressions of what it means to be human. There is another angle to this that almost never gets discussed openly, and it involves an uncomfortable truth about the nature of ambition and exploration. The drive to reach other stars is, in part, a displacement activity, a way of imagining a spectacular future that doesn't require doing the much harder, much less glamorous, but actually more impactful work of building civilization in the space that is actually accessible. Mars is real. We can get there. It will require extraordinary commitment and significant technological development, but it is within the conceivable range of human achievement in the coming century. And yet, in the public imagination, and in many discussions of humanity's space future, Mars gets less attention than the romantic vision of interstellar voyages. This is partly because interstellar travel is dramatic in a way that Mars colonization is not. Going to another star sounds like the premise of a science fiction epic. Going to Mars sounds like a very expensive engineering project. But the engineering project is real and the epic is not. This displacement matters because attention, funding, and intellectual energy are finite. Every decade spent fantasizing about interstellar propulsion systems we cannot build is a decade not spent solving the radiation shielding problem, the closed-loop life support problem, the in-situ resource utilization problem, and the artificial gravity problem that would make genuine solar system colonization possible. The opportunity cost is real. The most honest way to talk about interstellar travel is this. It is not impossible in principle, in the same way that it is not impossible in principle to construct a sphere of iron the size of the solar system. The physics doesn't forbid it, but it is impossible, in any practical sense, for beings of our biology with our lifespan, using our technology within any time frame that a human being or a human institution can meaningfully plan for. And the question of whether some future civilization of fundamentally different beings descended from humanity but transformed over thousands of years in ways we cannot predict might eventually develop the capability to travel between stars is genuinely unanswerable and therefore largely beside the point for any conversation about what humans should do now and in the next few centuries. Let's now talk about the specific, concrete reasons that converge from multiple independent directions, not just propulsion and biology, but economics, psychology, governance, and communication, all pointing toward the same conclusion. Because the robustness of this conclusion is part of what makes it so important to understand. The economic argument is simple and devastating. An interstellar mission, even the most stripped down, minimally crude, one-way colonization attempt, would cost on the order of trillions of dollars at minimum, and almost certainly many times more when the actual engineering realities are confronted. For comparison, the entire Apollo program, which sent 12 humans to the moon and back over 3 years in missions lasting at most 12 days, cost approximately $257 billion in today's dollars. The International Space Station, which has operated continuously since 2000, has cost roughly $150 billion to build and operate, shared across 20 participating countries. NASA's current budget is approximately $25 billion per year. A mission to send even a small crew to Alpha Centauri, even using propulsion systems that do not yet exist, would require a spacecraft orders of magnitude larger than the ISS, with propulsion systems that remain entirely theoretical, supporting human life for decades, hardened against radiation that we currently have no method to block, equipped with medical facilities capable of handling any emergency without external support, and carrying or manufacturing food for the entire voyage. The cost estimates that have been made in serious academic contexts are in the range of hundreds of trillions of dollars, roughly 10 to 100 times the current global GDP. This is not a cost that any conceivable government, corporation, or international coalition could bear, and it would require this expenditure with essentially no prospect of material return, because the destination is so far away that any resources found there cannot be returned to Earth within any economically meaningful time frame. It is not that money is the limiting factor, it is that the cost reflects the genuine difficulty. When an engineering task costs an amount that exceeds the entire productive capacity of human civilization by an order of magnitude, that is the economy telling you something profound about the task. It is not possible for the same reason that it is not possible to buy more than everything. The governance argument is similarly compelling. An interstellar mission lasting 40 years or 400 years or 4,000 years, depending on propulsion capability, requires institutional continuity that no human institution has ever maintained. The longest-lived continuous human institutions are certain religious organizations and a handful of governments, and even these have experienced fundamental transformations of identity, purpose, and leadership over centuries. The idea that a mission launched by one nation or one coalition of nations would remain funded, supported, and directed by that same institution 40 years later, when the mission is still in transit and has not yet delivered any results, is contradicted by every example from human political history. Consider that NASA's budget has fluctuated enormously over its history, driven by political priorities that have nothing to do with the scientific merits of space exploration. The Apollo program was largely abandoned after the immediate political objective of beating the Soviet Union to the moon was achieved. The Space Shuttle program, which was supposed to drastically reduce the cost of access to space, was instead cancelled after 135 flights when two disasters highlighted its inherent safety limitations. The Constellation program, which was intended to return humans to the moon and eventually send them to Mars, was cancelled after 6 years and billions in expenditures. These programs lasted years, not decades or centuries. The possibility that any human government or institution could maintain consistent support for an interstellar mission over the time spans involved is not just unlikely. It is essentially impossible given everything we know about how human political systems work. Priorities change, leadership changes, crises arise, wars occur, economic downturns reduce available resources, and the mission keeps going, consuming resources, delivering no results yet, and requiring increasingly uncomfortable decisions about how to respond when something goes wrong. Then there is the communication argument, which is perhaps the least intuitive, but in many ways the most fundamental. Communication between the spacecraft and Earth would become slower and slower as the mission progressed, eventually becoming so slow that the relationship between mission control and the crew would transform from something resembling management to something resembling archaeology. 4 years and 3 months one way at Alpha Centauri means that anything mission control wants to communicate to the crew must be planned more than 4 years in advance. If a crisis develops aboard the ship, mission control learns about it 4 years after it happened. The crew has already dealt with it or perished. Any advice that Earth sends in response arrives 4 years after that, now more than 8 years after the original event. The crew of an interstellar vessel is not an extension of a mission control team. They are an entirely autonomous civilization, making their own decisions, developing their own culture and values and priorities, evolving away from the parent civilization at a pace directly proportional to the communication delay. By the time they arrive at their destination, the mission control team that launched them will be retired or dead. The culture that created the mission will have evolved significantly. The instructions that were written for the mission will reflect priorities and values that the crew, having spent decades in an entirely different environment and situation, may not share. Who governs these people? No existing legal framework addresses this clearly. The Outer Space Treaty of 1967, which all spacefaring nations have signed, establishes that nations are responsible for their spacecraft and crew. but it was written entirely in the context of solar system missions. The concept of a spacecraft beyond the solar system, beyond the reach of any communication that could enforce any agreement, raises profound questions of governance that no legal philosopher or space lawyer has adequately resolved. A crew traveling to another star system for decades would develop their own customs, their own justice system, their own values. The idea that they remain legally and morally subject to the authority of a government on a planet they left behind decades ago and to which they can never return is philosophically incoherent. All of this leads to the uncomfortable but unavoidable conclusion that interstellar travel, even if physically achievable at some level of technology, would not be a mission launched by Earth and controlled by Earth. It would be the permanent separation of a group of human beings from human civilization, the creation of a new and alien community that shares our genetic heritage but becomes in every other meaningful sense something different. Whether you consider that tragic or inevitable or perhaps even beautiful, it is categorically different from exploration in any sense that humans have historically understood the word. Let's step back from all of these specific barriers and think about what they add up to. The distance problem is not going away. The energy requirement is not a technology problem, but a physics problem driven by the rocket equation and the fundamental nature of matter and energy. The biological problem reflects 4 billion years of evolution that shaped us for Earth and only Earth. The radiation problem reflects the structure of the universe's high-energy particle environment, which we did not create and cannot control. The psychological problem reflects the nature of human consciousness and social bonds and meaning-making, which cannot simply be engineered away. The institutional problem reflects the structure of human political and social organizations, which operate on timescales incompatible with interstellar missions. The communication problem reflects the speed of light, which is not negotiable. Every single one of these barriers is independent of the others. Solving one doesn't solve any of the others. To have any hope of genuinely sending humans to another star system, you would need to solve all of them simultaneously, and the solution to each one would be so transformative that the beings capable of applying those solutions would barely be recognizable as human in any meaningful sense. They would be post-biological, capable of surviving without the physiology that currently defines human limitation. They would be post-economic, operating outside any resource constraint we can currently model. They would be post-institutional, organized in ways that transcend the political structures that currently determine how human projects are funded and governed. They would be traveling in vehicles built with materials and using propulsion systems based on physics we don't yet understand. In short, they would not be us. This is perhaps the most honest answer to why humanity will never leave this solar system. Because by the time anything like interstellar travel becomes possible, the beings doing it will not be what we currently mean when we say humanity. Whether we consider that a tragedy or a triumph or simply an observation depends on how you define the word. And here is where something genuinely profound emerges from this entire discussion. The fact that the stars are forever beyond our biological reach is not a reason for despair. It is, in a sense, a definition. It defines what we are. It defines the scale at which human meaning is created and experienced. The stars are not places we will go. They are things we will know. We will understand them, map them, characterize them, discover the planets around them, search for signs of life in their atmospheres, and wonder about what walks or crawls or swims or breathes or thinks on surfaces we will never touch. That is not a lesser form of engagement with the cosmos. It is the form of engagement available to beings of our nature, and it is magnificent. We have been doing astronomy for thousands of years, discovering new depth and new complexity with every advance in technology, and the process shows no sign of reaching a limit. Every new telescope reveals new phenomena. Every new detector opens a new window on the universe. The James Webb Space Telescope is currently sending back images of galaxies that formed when the universe was less than 300 million years old, over 13.5 billion light-years away. We are seeing, in detail, the infancy of the cosmos. We are not going there, we are seeing it, and seeing it, understanding it, connecting it to the laws of physics and chemistry and biology that we have worked out over centuries of scientific inquiry is one of the most extraordinary things any mind in the universe has ever done. The solar system itself, which is often treated as just the neighborhood you pass through on the way to somewhere more exciting, contains enough mystery and complexity to occupy human scientific and exploratory attention for centuries, possibly forever. We have visited every planet with robotic spacecraft, and in nearly every case, what we found was startlingly different from what we expected. Jupiter's Great Red Spot, which was assumed to be slowly dying, turns out to be maintained by smaller storms being absorbed by the larger one. The Saturnian moon Enceladus, which appeared to be a small, geologically dead ball of ice when viewed through Earth-based telescopes, turns out to be actively erupting material from a subsurface liquid water ocean. Pluto, which everyone assumed was a frozen, geologically dead dwarf planet, turns out to have mountains of water ice, nitrogen glaciers, complex atmospheric hazes, and possibly subsurface liquid water. Titan, Saturn's largest moon, turns out to have liquid hydrocarbon lakes, dune fields, and an atmospheric chemistry so complex that scientists have identified hundreds of distinct organic molecules and have only begun to understand how they are created and how they interact. Every time we look more carefully, we find more. This pattern has held for the entire history of astronomy and planetary science, and there is no reason to think it will stop. The outer solar system alone, beyond Neptune, contains thousands of known objects and almost certainly millions that we have not yet catalogued. The Kuiper Belt and scattered disk are poorly characterized. The Oort cloud, which we believe contains billions of icy objects in a sphere extending nearly 2 light-years from the Sun, has never been directly observed. We infer its existence from the trajectories of long-period comets that fall inward through the solar system, but we have never sent a spacecraft there, and the thought of what we might find if we did is genuinely exciting. The ice giants, Uranus and Neptune, are among the least well-understood planets in the solar system, despite being the most common type of planet in the Milky Way. We know from exoplanet surveys that planets with masses between Earth's and Neptune's appear to be extraordinarily common around other stars, and yet we have visited them only once each, with Voyager 2's flybys in 1986 and 1989. NASA is currently developing a concept for a Uranus orbiter and probe mission, and the scientific return from such a mission could reshape our understanding of ice giant planets across the galaxy, which is directly relevant to evaluating the habitability of many of the potentially Earth-like worlds we find around other stars. And then there is the most profound mystery hidden within the solar system, one that could be resolved without leaving it and would represent one of the greatest discoveries in human history: the question of whether life exists beyond Earth. We live in a solar system that contains, within the easily accessible gravitational neighborhood of the Sun, at least several environments where liquid water exists or has existed, where organic chemistry is occurring, and where energy sources adequate to support biology appear to be present. Mars had a warmer, wetter past. Liquid water may exist in underground aquifers on Mars today, kept liquid by geothermal heat. Europa's subsurface ocean is large, has existed for billions of years, and may have hydrothermal vents where chemistry resembling that which may have given rise to life on Earth is occurring right now. Enceladus's ocean contains organic molecules and active chemistry. Titan's atmosphere is producing complex organic compounds that rain down onto a surface where, in its methane lakes, entirely different chemistry may be generating the building blocks of something resembling biology. If we find life in any of these places, even microbial life, even fossils of life that existed billions of years ago, the implications for our understanding of biology, of chemistry, of the universe would be revolutionary. It would mean that life arose independently at least twice in the same solar system, and by extrapolation would almost certainly mean that life is ubiquitous throughout the galaxy. We would know, not speculate, but know that biology is a natural consequence of chemistry given the right conditions, and that the right conditions are common in the universe. The question of whether we are alone would be answered in a way that would reshape philosophy, religion, science, and the human sense of place in the cosmos, perhaps more profoundly than any other discovery in history. And we can find that answer not by leaving the solar system, but by going deeper into it, by sending the robots and eventually the humans needed to drill through the ice of Europa and Enceladus and lower instruments into the oceans below, by sending the laboratories and the time needed to search every promising environment within Mars's crust for the chemical signatures of past or present biology. By characterizing Titan's chemistry in the detail needed to understand whether any of its reactions bear the hallmarks of metabolic processes. This work is the real work ahead of us. This is the genuine frontier of discovery, not 4 light years away, but right here, within a few billion miles, in an environment we already know enough about to plan missions to and to which the journey times are measured in years rather than millennia. Let's also address the argument that humanity needs to become a multi-planetary species for reasons of existential risk management. This argument is made often and sincerely, and it is correct in its premise. Concentrating all of human civilization on a single planet does expose our species to a single-point failure that could be catastrophic. A sufficiently large asteroid impact could destroy all complex life on Earth. A global pandemic could theoretically reduce the human population below the level needed to maintain civilization. A nuclear exchange involving the world's major nuclear powers could create a nuclear winter. Climate change, left unaddressed, could make large portions of Earth uninhabitable and destabilize civilization on a global scale. These are real risks, and the intuition that distributing human civilization across multiple bodies makes it more robust is entirely correct. But the solution to these risks does not require leaving the solar system. It requires becoming a genuinely multi-world civilization within the solar system. A permanent human presence on Mars, even a small one of a few hundred people, would mean that human civilization could survive the total destruction of Earth for the first time in our history. A population of thousands on Mars, with the ability to sustain themselves independently of Earth for extended periods, would make the extinction of human civilization essentially impossible by any natural event. A network of habitats in the asteroid belt and beyond would make it even more robust. The existential insurance policy that interstellar advocates argue for as a reason to reach other stars is actually achievable, and achievable far sooner within the solar system. The only risk that solar system civilization cannot fully address is the death of the Sun itself, but as we have already discussed, that event is approximately 5 billion years away, and planning for it now is not rational for the same reason that making funeral arrangements for an infant is not rational. Now let's return to the title of tonight's conversation, the real reason humanity will never leave this solar system, and synthesize everything we have discussed into the clearest possible statement of what that reason is. It is tempting to say the reason is the distance. That is true, but incomplete. It is tempting to say the reason is the energy requirement. Also true, also incomplete. It is tempting to say the reason is our biology, our radiation sensitivity, our bone loss, our psychological fragility. True, incomplete. The real reason is more fundamental than any single barrier. The real reason is that all of these barriers, independently derived from different branches of physics and biology and psychology and economics, all point in the same direction, simultaneously. When multiple independent constraints all push toward the same conclusion, That convergence is not a coincidence. It is the universe telling you something. What the universe is telling us is this: life, biological life as we understand it, exists at a specific scale. It operates at specific energies, temperatures, timescales, and distances. It evolved on planets sustained by stars at specific orbital distances within specific gravitational and electromagnetic environments. The machinery of biology, with its hydrogen bonds, its enzyme kinetics, its nervous system signal propagation speeds, its heartbeats and breaths and sleep cycles, is calibrated for planetary scales. It is not and has never been calibrated for interstellar scales. The gap between those scales is not just enormous, it is fundamental. This is not a tragedy, it is a definition. We are not stellar beings, we are planetary beings. We emerged from a planet, we are made of a planet's chemistry. We experience the universe at a planet's scale and at a planet's pace. The stars are our context, not our destination. They are what we look up at, not what we travel to. And in that looking up, in that wondering, in that extraordinary capacity to comprehend distances and times that we can never personally experience, there is something genuinely wonderful about what it means to be human. Carl Sagan wrote in his description of the photograph of Earth taken by Voyager 1 from 4 billion miles away, that our planet is a mote of dust suspended in a sunbeam, that all of human history occurred on this tiny world, and that in our obscurity, in all of this vastness, there is no hint that help will come from elsewhere to save us from ourselves. He was trying to communicate humility and responsibility. But there is another reading of that same photograph, that everything which has ever been beautiful, everything which has ever been heroic, everything which has ever been loving or noble or terrifying or hilarious in human experience, all of it happened here, on this one blue speck, sustained by one ordinary star, in one spiral arm of one galaxy among trillions. And it happened at all. Against the cold indifference of a universe that mostly consists of empty space and radiation and slowly cooling hydrogen, this happened. We built the Parthenon and the Great Wall and the Alhambra. We composed the Ninth Symphony and the Goldberg Variations. We wrote the Iliad and King Lear and 100 Years of Solitude. We developed the germ theory of disease and the theory of evolution and general relativity and quantum mechanics. We invented the microprocessor and the internet and the DNA sequencer. We sent 12 men to walk on the moon and brought them home safely. We flew robots to every planet and found moons with liquid oceans and worlds with nitrogen glaciers and moons with hydrocarbon lakes. We pointed a telescope named after the space scientist Lyman Spitzer toward the oldest light in the universe and found galaxies forming when the cosmos was 2% of its current age. All of this happened on a mote of dust. All of it will continue to happen on a mote of dust, and eventually on a few nearby motes of dust, and perhaps eventually on motes of dust throughout this solar system. And the stars will remain where they have always been, beautiful and incomprehensible and impossibly far away, as they have been for as long as anything capable of appreciating beauty has existed. This is not the end of the story, it is the correct chapter. It is the chapter where beings made of chemistry, bound to planetary scales, discover the deepest truths of the universe, not by traveling to it, but by understanding it, by building instruments that can see it, by developing mathematics that can describe it, by sustaining civilizations that can pass that understanding from one generation to the next, accumulating knowledge across centuries in a relay that is itself one of the most remarkable phenomena in the known universe. The real reason humanity will never leave this solar system is simple, and it is not a failure. It is the universe organizing itself in such a way that life emerges at planetary scales, and minds that can comprehend stellar scales emerge from that life, and those minds then spend eternity trying to close a gap between what they can understand and what they can reach. We can understand to the edge of the observable universe. We can reach to the edge of the solar system. That distance between understanding and reaching is not a flaw in our design. It is the fundamental shape of our consciousness. We are here on this small blue world, orbiting this ordinary star, staring up at a sky full of impossible distances. And instead of being crushed by those distances, we mapped them, we measured them, we named the stars and catalogued their spectra and counted their planets and searched their light for the chemical signatures of other worlds that might harbor other minds. And we are still staring, still measuring, still naming, still wondering, and we will keep doing this for as long as human beings, or whatever we become, exist to do it. Let's not end there, though. Let's look at what this means practically for the actual decisions that actual human beings and human institutions will make about space in the coming decades, because there is something deeply useful in understanding where the real frontiers are. The decision of whether to focus space exploration resources on interstellar ambitions versus solar system development is not merely an academic one. It has real consequences. Billions of dollars in research funding are allocated every year toward various aspects of space technology, and the framing of humanity's space future significantly influences where that money goes. If the dominant narrative is that the solar system is just a launching pad and that our real destiny lies at the stars, resources tend to flow toward speculative propulsion research, toward laser sail concepts, toward theoretical physics of warp drives and wormholes, all of which is scientifically interesting, but none of which moves us closer to the actual immediate frontier of making human civilization genuinely multiplanetary. If instead the dominant narrative is that the solar system is the actual frontier, that there is extraordinary science and extraordinary discovery and extraordinary human potential to be unlocked within the gravitational reach of our sun, the resource allocation changes significantly. Investment goes toward radiation shielding technologies that would actually enable humans to live on Mars and in the asteroid belt. Investment goes toward closed-loop life support systems that would actually sustain human beings away from Earth for years and decades. Investment goes toward in-situ resource utilization that would actually make space presence economically sustainable rather than dependent on continuous resupply from Earth. Investment goes toward the heavy-lift launch vehicles and propulsion systems that would actually get humans and their equipment to the places where the real scientific questions are waiting to be answered, which is throughout this solar system. We are at an interesting moment in space history. For the first time since Apollo, there is a credible commercial sector investing serious capital in space transportation. SpaceX has reduced the cost of launch to low Earth orbit by an order of magnitude compared to what it was 20 years ago. Blue Origin and other companies are developing their own launch vehicles. NASA is developing a program to return humans to the moon under Artemis. The United Arab Emirates and China have both sent successful missions to Mars. Japan and India have successful lunar missions. ESA and NASA are developing a Europa Clipper mission to perform detailed flybys of the Jovian moon, most likely to harbor life. The pace of robotic exploration is genuinely accelerating. What is needed now is the clarity of vision to direct this growing capability toward the actual immediate goals, the ones that are achievable, the ones that will genuinely transform what humanity is and what humanity knows, rather than the romantic but physically inaccessible goal of flying to another star. We need humans on Mars. We need a systematic search for life in the subsurface oceans of icy moons. We need detailed characterization of the asteroid belt and eventually the establishment of robotic and then human industrial presence there. We need the exploration of the ice giants and their moons. We need missions to the Kuiper belt and eventually to the inner Oort cloud. We need the expansion of humanity's physical presence throughout this solar system, None of this is easy. All of it is hard in ways that will push our engineering, our science, our institutional capacity, and our personal courage to their limits. But all of it is within the reach of beings who can walk upright under gravity, breathe air, eat food, form social bonds, and die of old age. It is within the reach of humans. The stars are not, and that is all right. There is a kind of arrogance in the assumption that our destiny must be cosmic in scale, that the appropriate measure of human achievement is the distance we can physically cover, that what we are doing here on this planet and within this solar system is somehow inadequate as long as the stars remain beyond reach. That arrogance misses the actual point of what has been happening for the past 4 billion years, which is that complexity and intelligence and beauty and meaning have emerged in a particular corner of a particular solar system, and that they are worth understanding and protecting and developing, not as a stepping stone to somewhere grander, but as the thing itself, the most extraordinary thing that has happened in this part of the universe. Life, mind, wonder. We are the solar system becoming aware of itself, not more than that, but not less. Every civilization that has ever existed, every human being who has ever lived, every idea that has ever been thought, every art that has ever been made, every truth that has ever been discovered has happened within the gravitational reach of one star. And there is more to discover here, in this system, in this neighborhood, than any civilization could exhaust in 1,000 generations. So perhaps the most important thing to understand about humanity and the solar system is not that we will never leave it. It is that we have barely begun to know it. And that is where the real adventure is. Not in the direction of the nearest star, which is impossibly far, but in the direction of the next moon, the next asteroid, the next frozen world in the outer dark that we have seen only briefly and only from afar. In the direction of the ocean beneath Europa's ice, which no human eye has ever seen, and which may contain the answer to the oldest question any mind in the universe has ever asked. Are we alone? That answer is here. The question is whether we have the wisdom to look for it in the right place, at the right distance, within the reach of the only kind of beings that have ever, in all of human knowledge, been known to exist.
We are those beings. We are here. And this solar system is ours, not to escape, but to explore, to inhabit, to understand, completely, deeply, honestly. For as long as there are minds to do the exploring, the stars can wait. They have been waiting for 13.8 billion years already. They are not going anywhere.
We are the ones who need to figure out where we are going. And where we are going is here. Deeper into here. Into this magnificent, strange, haunted, beautiful, and still mostly unknown solar system that gave us everything we are. Good night, and thank you for exploring this with me tonight. The question we started with was simple. Why will humanity never leave this solar system? And what we found was something more interesting than a limitation. We found a definition of what it means to be alive, to be curious, and to be human in a universe that is vast beyond anything our biology was ever designed to comprehend, and yet not vast beyond anything our minds were designed to imagine. There is a dignity in that. There is even a kind of freedom. The nearest star is 24.9 trillion miles away, and we know exactly what that number means. If this changed how you think about our place in the cosmos, about what space exploration truly means, about where humanity's real frontier actually lies, then the time was well spent. Thank you for staying with me through this long journey. The universe does not give up its most important truths quickly. Keep looking up. The answers are here.